We have an example of a limit question here involving an absolute value bars. I always tell you, no matter what, even though right now when I see these absolute value bars, I pretty much know 99 times out of 100 what my method's going to be. It's going to be using our absolute value method. But I always tell people you can't forget option one, which is just going to be to plug it in, because every time you go to think it's not going to work, it'll end up working. So option one, you always just plug that value in for wherever you see that variable in the equation and see what you get out. Sometimes you're lucky and you're done. That is your answer. Sometimes you're unlucky and guess what? You get to do more work. And so here, whenever I go to plug a value in, that's the point when I can cancel out my limit statement. So I drop the limit statement. I start plugging in -1 everywhere. And what I'm going to see is that I'm going to get on top 1 minus 1 is going to get me 0. On bottom 2, -2 plus 2 is going to give me 0. And so what I see is I get division by 0. So this is bad. We are not allowed to divide by 0. And so we know that option 1 fails us. What we now need to look for is our next available option. And as I said at the beginning of the video, as soon as I see the square root, I know I need to use this absolute value method. And the absolute value method is about breaking this problem up into two separate problems. And so why we're going to break this up into two separate problems is really because of how the graph of an absolute value function behaves. So if you think about your standard absolute value graph, which is just a V that sort of bounces right here. So this is the graph of the absolute value of x. Well, when you break this up, what you really get on this right-hand side, this is really the graph of y equals x. And on the left side, this is the graph of y equals -x. And so that's how you're going to break this thing up. We're going to break it up into the left side equation, which is going to be based upon this left side piece right here, the idea that y equals -x. And then we're going to do a right side, a right-hand limit, and that's going to be based upon the idea that the right-hand side is the same as this graph y equals x. And so how we apply that here, you take your limit, and so on this left side I'm going to have limit as y approaches -1, and then from the left direction, nothing happens to that y squared minus 1 on top. But when I go to rewrite the bottom now, I rewrite it using the idea that it's negative whatever is inside those absolute value bars. So this is negative and then parentheses always. If you drop those parentheses, you'll be off by a sign. So that's how we'll rewrite the left side. And then on the right side, we'll do the same type of game. We'll do limit as y approaches -1, and then from the right, we put our little plus sign in there. The top of this stays the same, but to get out of those absolute value bars, it's that right-hand side. It's the y equals x. And so on the right side, we literally just drop the absolute value bars. And that's our brand new math problem. And so because we're dealing with an overall limit in this problem, what we end up doing is finding the left-hand limit on the left side, finding the right-hand limit on the right side, and then comparing those two to see if they're the same. Or if they're different, then the overall limit does not exist. What we've stepped into now, you basically have to treat them like two brand new problems. So option 1 failed. It gives us division by 0. But if we look here, we're kind of seeing this difference of two squares. We're seeing a squared option up on top. And so what we're going to do is we're going to go to our factor and cancel method. So this will be limit as y approaches -1. And then that difference of two squares factors out to be y plus 1, y minus 1. You have to be able to recognize the difference of two squares. It shows up everywhere. On the bottom of this, though, what we can see is that there's a 2 in both of these pieces here. And so we can factor a 2 out of the bottom. So we'll pull a 2 to the front with that negative sign, and that'll leave us with y from the first term. And then when I pull a 2 out of a 2, I'm still left with a 1. So we've done our factoring, and then, oh, look what we see. Y plus 1 cancels out with y plus 1. This type of cancellation is going to happen all the time on these problems, or else you probably messed up your algebra someplace. So -1 from the left. Cleaning this up, we have y minus 1 left on top, and on the bottom we have negative 2. And so at this point, you're just going to go ahead and back to option 1, plug it in. So we're going to get out of here, plugging in negative 1 everywhere we see a y. This is going to equal, we're plugging in so we can drop that limit statement. So negative 1 minus 1 over negative 2. So our left-hand limit, we get negative 2 divided by negative 2, so we are looking at a positive 1. So that is our left-hand limit. And now you're just going to go play the exact same game with this right-hand limit over here. It's a little bit easier because we don't have that negative sign, and it's a little bit easier because basically the same steps apply here, right? It's the same equation, just with one little negative sign. So coming at it from the right, we still do our difference of two squares factoring, so y plus 1, y minus 1. On the bottom, we can see that we've got a 2 that we can again factor out of everything. So we pull that 2 to the front, and we're left with y from the first term, plus, and then pulling 2 out of 2 leaves us with a 1 in the back. And then what do we see happen again? Miraculously, we get that cancellation that we were hoping for. Y plus 1 cancels with y plus 1. We rewrite what we have. Limit as y approaches negative 1 from the right. So on the top now we have y minus 1, and on the bottom we have 2. Back to option 1. Everything should end in option 1 if you've done it right. Almost always. So we go and we take our negative 1, plug it in whenever we see a y. We're plugging in, so we drop the limit statement finally. So negative 1 minus 1 over 2. That's going to get us negative 2 on top divided by 2 on bottom. So here we end up with negative 1. The final move on an overall limit question is you've got to come through and you have to decide, are those two things equal or are they not equal? And so here what we find is that these two things are not equal. And what that tells us is that our overall limit DNE does not exist. So the limit as y approaches negative 1 of y squared minus 1 over the absolute value of 2y plus 2. The answer to that is that the limit DNE does not exist.